Hey there, and welcome back to The Explainer. Today, we are taking a journey into what is honestly the ultimate internet upgrade. We're talking about the invisible plumbing of the entire digital world. You know, for decades, the internet relied on this foundational protocol to just get your data from point A to point B. But what happens when that foundation literally runs out of room? Well, we're going to explore this massive, silent migration that's happening right under our noses, and look at how it completely changes the way networks are actually built.
Now, did you know the internet actually ran out of addresses back in 2015? I know, it kind of sounds like an internet myth, right? But it's completely true. Back in the summer of 2015, ARIN, that's the registry responsible for North America, literally handed out its very last block of IPv4 addresses. The original 1980s design gave us roughly 4.3 billion public addresses, and sure, that seemed like an infinite amount back then. But with smartphones, smart TVs, IoT devices everywhere, we burned right through that supply. We used short-term fixes like network address translation to buy us some time, but we needed a true permanent fix. Enter IPv6 or IPv6.
All right, let's dive into the math here, because IPv6 solves this global crisis with pure overwhelming numbers. While IPv4 addresses are 32 bits long, an IPv6 address, it is a staggering 128 bits long. We are jumping from a space of 4.3 billion addresses to a number so massive it's honestly hard to even comprehend. It's literally enough to assign an IP address to every single grain of sand on Earth, several times over. So yeah, permanent fix? Absolutely.
But here's the catch. We've got this giant 128-bit address now. How do we fit that on a screen without completely losing our minds? That's a real challenge for network engineers. If you tried to write out 128 ones and zeros, your eyes would just glaze over before you even finish the first line. So, to make this actually readable for us humans, IPv6 completely ditches that old dotted decimal format we used in IPv4. Instead, it uses hexadecimal format.
To make this work, an unabbreviated IPv6 address is made up of 32 hexadecimal digits. We take those digits and organize them into 8 groups of 4, which we usually call quartets. And instead of using little periods, we separate these quartets with colons. You can think of it kind of like an extremely long, rigid international phone number. It's highly structured, sure, but admittedly, typing out 32 digits every single time you configure a router, yeah, that is a total recipe for typos.
Thankfully, the designers knew we'd need some shortcuts, and this brilliantly illustrates how they plan for human efficiency. We basically have 2 golden rules to abbreviate these massive addresses, kind of like texting shorthand. Step 1, you can completely drop the leading zeros in any quartet. So 0100 just shrinks down to 100. Step 2, if you've got a consecutive sequence of quartets that are all zeros, you can replace that whole chunk with a double colon. You only get to use that double colon trick once per address, but man, it magically shrinks these intimidating numbers down into something way more manageable.
All right, so we can write the address without our hands cramping up, but how do we organize a global internet made of these things? That's the next big puzzle. If every single device gets a unique address, routing all that traffic would be an absolute nightmare unless we organize it logically. So, we really need to talk about IPv6 subnetting.
Think of a global unicast address like mailing a letter, broken down into 3 specific parts. First, the global routing prefix. This is assigned by your ISP, and it acts almost like an international zip code that directs traffic straight to your specific company. Next is the subnet ID, which is controlled by the local network engineer. That's like picking the specific floor or department in your building. And finally, the interface ID, which pinpoints the exact room or computer.
And what I absolutely love about this is the interface ID. In almost all standard deployments, this field is exactly 64 bits long. By locking the interface ID to the right-hand 64 bits, it splits that 128-bit address perfectly down the middle. For any network engineers out there who used to pull their hair out over crazy IPv4 subnet math, this /64 prefix length makes subnetting just incredibly clean and straightforward.
But hold on a second. If we have enough addresses to give literally every light bulb in your house a public IP, should we? Does your office printer actually need a globally reachable internet passport? The short answer is no. IPv6 is actually smart enough to know that different devices need different levels of communication.
So the crucial point here is that IPv6 has distinct address types for specific jobs. Global unicast addresses are your public IPs. Those generally start with a 2 or 3. Then we have unique local addresses, starting with FD. Those are completely private and don't route onto the public internet at all. Next are link local addresses, starting with FD80.
These are highly specialized and only used for devices communicating on the exact same local subnet. And finally, multicast addresses starting with FF, which let you send packets to multiple destinations all at once.
Okay, so we've mastered the whiteboard math. We know the formats, the abbreviations, the address types, the whole shebang. But networking isn't just theory, right? Eventually, you actually have to sit down at a terminal and configure a physical piece of hardware. So how does a Cisco router actually handle all this?
Well, here is the physical reality. These complex protocols run on sprawling server racks and miles of physical cabling. And remember, we didn't just unplug IPv4 on a Friday and plug in IPv6 on a Monday. It's an ongoing gradual migration using a strategy we call dual stack. This basically means the router's interfaces are actively configured with both an IPv4 address and an IPv6 address, processing both types of traffic at the exact same time on the exact same physical wire.
Now, to wake up a Cisco router and get it speaking IPv6, you need two vital commands. Step 1 is one that beginners forget all the time, IPv6 unicast-routing. See, while IPv4 routing is on by default, IPv6 routing is actually turned off right out of the box. You have to turn the engine on globally first. Then, step 2 is assigning the address to the specific interface using the IPv6 address command followed by your prefix. And boom, your router is officially in the IPv6 game.
All right, so your router is alive and kicking. It's got its brand new 128-bit address. But a router just sitting there in isolation isn't exactly useful. It needs to forward traffic to its next hop neighbors. In the old IPv4 days, devices used a protocol called ARP. ARP basically blasted broadcast messages to everyone on the network yelling, "Hey, who has this IP address?" But broadcasts are super noisy and inefficient, and honestly, IPv6 kind of hates broadcasts.
To fix this, IPv6 completely replaces ARP with a sleeker, far more efficient system called the Neighbor Discovery Protocol, or NDP. Instead of shouting to the entire room with a massive broadcast, NDP uses targeted multicast. It basically just taps the shoulders of the specific devices that actually need to hear the message. It is a massive, massive upgrade in network efficiency.
NDP handles all this network mapping using 4 specific messages. If a host needs a MAC address, it sends out a neighbor solicitation and the target replies back with a neighbor advertisement. But it gets even cooler. Hosts can also actively look for routers by sending a router solicitation. The local router then replies with a router advertisement, essentially saying, "Hey, I am your gateway, and here is the network prefix we're using." Now, what's truly mind-blowing about this process is a feature called SLAC. That's Stateless Address Auto Configuration. Thanks to those router advertisement messages we just talked about, an IPv6 host can literally build its own IP address. It listens to the router announce that 64-bit network prefix, and then it automatically generates its own 64-bit interface ID to snap right onto it. It dynamically maps itself onto the network without ever needing to talk to a centralized DHCP server. It is basically plug-and-play networking on a massive scale.
Finally, to tie this whole connection process together, when you configure an IPv6 address on an active router interface, the router automatically injects 2 critical entries right into its routing table. First, it adds a connected route for the /64 subnet, telling the router exactly where that network lives. And second, it adds a local route with a /128 prefix. Now that /128 means exactly this one single address, which ensures the router knows its own specific identity on that interface.
And that brings us to the big picture here. We've moved from a cramped 32-bit world to a virtually limitless 128-bit space. We've completely replaced noisy broadcasts with elegant, targeted multicasts. And we now have devices that can dynamically stitch themselves into a network using SLAC. If our very infrastructure is becoming this self-aware and automated, what entirely new possibilities is this going to open up for the networks of tomorrow? Something to definitely think about as you continue mastering the network. Thanks so much for exploring this explainer with me, and I'll see you next time.